I'm Adam from RFOXiA from our real lab. Today we're answering how does a 57 by 47 millimeter module fit into space-constrained builds without giving up any of the performance specs that made it worth using in the first place. Enjoy our new soundtrack at the end of the video. Size is a constraint that engineers underestimate until it costs them a board revision. I want to talk about that, specifically about what the 57 mm by 47 mm footprint of the Multinav Pro Plus BLE module means in real integration scenarios, and why the decisions that produced this form factor were not straightforward. Let me start with what 57 by 47 actually is. It is smaller than a standard business card. It is smaller than the palm of most hands. It is a size category that in the BLE module market typically comes with a trade-off. You get the small footprint and you give up range or data rate, or you accept a non-certified component that you cannot ship in a commercial product without going through certification yourself. That trade-off is the market convention. The Multinav Pro Plus does not follow it. The reason I want to explain the design philosophy before I show you the hardware is that the size did not come for free. Fitting a high-gain chip antenna, an STM32WB07 CCV6 dual-stack processor, the RF front-end circuitry, and 4 distinct interface headers, GNSS, sensors, motor and battery management, and programming, onto a board this size required making actual engineering decisions about component placement, ground plane geometry, and antenna clearance. None of those decisions were obvious. Some of them took multiple board spins to get right. The antenna is the most constrained element. The chip antenna on this module is 140 mm long. That is longer than the module itself in one dimension. The placement relative to the RF circuitry and the ground plane boundary affects radiation pattern and ultimately affects range. If the antenna is too close to copper core, you detune it. If the clearance zone is not respected in the host board layout, you lose sensitivity at the receiver. And receiver sensitivity is the single most important specification on this module. The -104 dBm sensitivity figure is not a datasheet aspiration. It is what you get when the RF design is correct. It is also the first thing that disappears when the layout is wrong. This matters for you as an integrator because the fixing frame holes, 54 mm by 34 mm at the corners, tell you exactly how much board real estate you are committing to. But the antenna clearance zone extends beyond that. When you are designing the host board, you need to respect the keep out area around the antenna. I will cover this in the integration documentation, but the practical summary is the module is 57 by 47 and the total area you need to reserve, including antenna clearance, is larger, not dramatically larger, but larger. Plan for it. Now, why does any of this matter in the specific context of space-constrained builds? Because the builds where physical size is the deciding constraint are also the builds where you cannot compromise on performance. A drone is the clearest example. A racing quadcopter or a long-range fixed wing has strict weight and volume budgets. The electronics bay is small. The module needs to fit in that space and also needs to function at 15 to 20 kilometers from the ground station when the drone is in the air. Those two requirements, small and long range, are in tension with almost every other BLE module on the market. At this form factor, with standard BLE chips, you get maybe 80 to 100 meters. That is a short drone flight. With the Multinav Pro Plus, at this same form factor, you get the full performance envelope. That is the engineering result that took the most time to get right. Robotics builds have similar constraints. A ground robot has an electronics enclosure. That enclosure has a defined volume. When you are integrating wireless communication, GNSS, environmental sensing, and motor control into that enclosure, the board stack height and the individual module footprints determine whether the system fits at all. The Multinav Pro Plus ecosystem was designed with this in mind. The BLE module, the GNSS module, the sensors module, and the power kit are designed to connect to each other directly through their interface headers. That means you are not running loose wires between boards. You are building a stacked assembly that is mechanically stable and electrically clean. The footprint of each module in the stack was specified to work together. Compact IoT enclosures present a different version of the same problem. When you are deploying a node in the field, on a lamppost, inside a junction box, on agricultural equipment, the enclosure size drives cost and installation complexity. A smaller module means a smaller enclosure means lower cost per node across a network of hundreds or thousands of units. At that scale, the 57 by 47 footprint is not an aesthetic choice, it is an economic one. The FCC certification on this module also deserves mention in the context of size-constrained builds. FCC certification means you can integrate this module into a commercial product without recertifying the radio. For a small team or an independent developer building a product that needs to ship, that is a significant reduction in both cost and time. The alternative, building your own RF design at this performance level and taking it through FCC certification from scratch, is a process that takes months and costs tens of thousands of dollars. The module eliminates that entirely. In a space-constrained build, having the certification already complete means you are solving fewer problems simultaneously, which matters when the enclosure design is already your primary constraint. The 2 megabits per second data rate is relevant here as well. At this module size, you would expect to make compromises on throughput to preserve range. The STM32WB07 CCV6 does not require that trade-off. The dual stack architecture runs the BLE stack and user applications on the same processor without the performance degradation you see on less capable chips running a shared core at equivalent clock rates. The practical result is that you can stream real-time sensor data, GPS coordinates, and control signals simultaneously at full rate without latency that would make the system unreliable for its intended application. In a drone, that means your telemetry and your control link coexist without competing for bandwidth. In a robotics build, it means your sensor fusion pipeline and your communication layer are not throttling each other. I want to be direct about what this module is not. It is not the right choice if your only constraint is cost and you need 10 meters of range to reach a nearby gateway. For that application, a commodity module at $3 that covers why the form factor decisions were made the way they were and what they mean for integration. Now let me show you the actual hardware. This is the range case for the 57 by 47 millimeter footprint, up to 50 kilometers drone to drone, 20 kilometers man to drone, 5 kilometers ground to ground, all from a board smaller than your palm with no licensed spectrum and no external infrastructure. 2 megabits per second at this form factor is not an accident. The RF design and the STM32WB07 CCV6 processor together eliminate the bandwidth bottleneck that limits smaller, cheaper modules. Sensor data, GPS, and control signals coexist on one link without competing. The STM32WB07 CCV6 runs the BLE stack and user applications simultaneously without architectural compromise. On a module this size, that dual stack capability is what allows full performance without a second processor, a second board, or a second power rail. 57 by 47 millimeters with a 140 mm chip antenna and fixing frame holes at 54 by 34 mm. This is the actual footprint you are committing to. Every millimeter of it was placed to preserve RF performance while leaving room for the 4 interface headers. The 4 interface headers, GNSS, sensors, motor and battery management and programming, are the reason this module stacks directly with the rest of the Multinav Pro Plus ecosystem. No loose wiring, no custom adapter boards, 1 mechanical assembly, 4 functional layers. The RFOXiA Connect app gives you a live map, sensor data, and a PS5 style controller interface from your phone to the module. The entire control and monitoring layer works at full BLE range, completely without internet. This is what the hardware unlocks at the application level. BLE Chat uses the module as a direct communication node between users. No towers, no internet, no subscription. Text, voice, and calls at the same range the module delivers for everything else. In a space-constrained build, the radio that handles your telemetry also handles your team communications. Full open source access and SWD programmability mean this module is a starting point, not a ceiling. You can write directly to the STM32WB07 CCV6, customize the BLE stack behavior, and build firmware tailored to your specific integration scenario without waiting on a vendor. The integrated RTC Crystal handles timing synchronization for navigation and time-sensitive applications. On a module this small, having a precise hardware clock on board removes one more external component from your design. Less board space consumed, one fewer thing to get wrong. Multinav Pro Plus is the correct answer when you need range that commodity modules cannot deliver, when you need the FCC certification already done, when you need ecosystem integration without custom board design, and when the physical space you are working with is the actual limiting factor in your design. If all 4 of those are true, there is currently no other solution at this price point that addresses all of them simultaneously. That is the market gap that produced this module. It exists because I needed it and it did not exist.
Soldering iron at 2 a.m. Schematic on the wall. Every trace of decision every signal a call. They said the range was impossible, they said the price was wrong. I mapped the RF landscape, and I built where I belong. No towers holding me, no infrastructure fee, just fixing intention and a module that runs free. We are the makers, we push the signal past the edge. We build the future with our hands, on every rooftop, every ledge. 50 kilometers of silence and the data starts to flow. We are the makers, and we built this from below. From below. The firmament writes itself now. Describe it, watch it run. AI speaks the language of what we have begun. Sensors streaming in the field, earning while I sleep. Every note a heartbeat, every dead mind to keep. No limits, no permission, this technology belongs to us, and everything we build is true. 20,000 meters, and the signal holds its ground. No internet, no towers, no infrastructure found. Just a module and a maker and a vision that was real. This is what democratize means. This is how we feel. We feel